Alright, so let's look at solving a couple more problems. So for my class, if you're watching the video, you want to try these as warm-ups to yesterday. Okay. So I'm going to solve each of them two different ways. Suggestions on this one. Don't get intimidated. There's only one variable. Where's the variable? Well, right there. So that's just a number. So like, move stuff away from it. Now, so you could go 2 log of x equals, and add that number to the other side. And then if you want to get stuff away from x, you could take that 2 and do what with it? Well, it's multiplying, so I'm going to divide it on the other side. And then to crack open the logarithm, what do I use? What's the inverse operator? Exponential base, what this time? 10. So raise both sides to the 10 power, not multiply. So it's going to cancel out over here, and I'm going to get x as this weird expression, 10 to the log of 4 divided by 2, which I could stick in my calculator. So let's see. 10 raised to the log of 4, and then that's divided by 2. So looks like we got a nice even answer here. 2. Interesting. Let's see if we get that another way. It's another option. You guys should have those properties in your head by now, and they should be starting to be reflexive. You gotta put the 2, you gotta move the 2 though first, right? It's blocking things. Where should I put it, Josh? Yeah, I could move this 2 up here. Smart. And then you can put those logarithms together. Minus becomes division in log land. 2 logs becoming 1 log. And then I do that same strategy to get rid of logarithm base 10. I exponential it on both sides. So I get x squared over 4, because these cancel out. 10 to the 0 power is, of course, 1. I can multiply by 4, so I get x squared equals 4. And I square root both sides, and I get plus or minus 2. Now, this has an extraneous solution in it. This is the first time you see one. Do we get plus or minus 2 when we did it the other way? No, we just got just plus 2, right? Just 2. Negative 2 could be an answer here, but it's not. You go back to your original problem, didn't we have that? Let's go back and think about the shape of the logarithm. So we saw it once the other day. It's going to start getting ingrained in your mind. We're going to do a whole section on transforming them, but we've seen it a couple times already. If you remember, logarithms didn't have a horizontal asymptote like exponentials. They had a vertical asymptote. This is what a logarithm looks like, basically. Its domain is only 0 to infinity. Can you put negative numbers into it? No. So if I put this negative 2 into it right there, it's broken. If you do that in your calculator, in fact, it's going to throw an error. It's going to say error, because that's not in the domain. It's undefined. Does that make sense? So you have to think about that a little bit with logarithms. We're going to do one that's a little bit more involved today, too. Okay, 2 different ways to do that one. Let's look at the second one. So I think the easier way to do it is to recognize 125 and 125th are relatives. They're both powers of 5. Yeah, that's the easier way to do this one. In fact, 125 is 5 cubed, and a 25th is 5 to the negative 2nd power. Okay, nice. So this is x plus 3. This is 2x. So now power to power means multiply. So I've got 5 to the 3 times x plus 3, and 5 to the negative 2 times 2x. And then to get rid of exponentials with a base of 5, I can operate with a logarithm base of 5. Cancel it out. And so I get a nice algebra question. It's just negative 4x over there, right? So it's going to be 3x plus 9 equals negative 4x. Add this to this side, you get 7x. Subtract the 9. And x is negative 9/7. Okay? The other way to do it would have been to use logarithms. Let's do it that way. You could just ignore that fact right away. Sometimes you can't even do that. You could use logarithms right away. I'm going to use base 10. So I'm going to operate with base 10 on both sides. That lets me pull the powers down. Now that looks ugly. If you don't let it intimidate you, it's not that bad. It can be intimidating though. Put your like terms together. So I'm going to distribute over here. So I've got x log 125 plus 3 log 125. And over here I've just got that same thing. Like terms are those ones with x's in them. So I'm going to stick the x's on the same side and the thing without an x on the other side. This is just easy algebra. It just looks funky. So get over it. Okay? So I'm going to go x minus 2x. Forgot something. X log 125 minus 2x log a 25th. And then I'm going to subtract this one that way. These share an x, pull it out, remember its factor. Log 125 minus 2 log of a 25th equals a number over here. As long as you're clear on what's a number and what's got a variable in it, this is not hard if you don't let it intimidate you. And then this is all just one big number, isn't it? So you got a big number times x. If you want x by itself, how do you get rid of it? Divide. So you go x equals this other number divided by this great big looking, scary looking number. And for some reason, that's supposed to be negative 9/7. Doesn't look like negative 9/7, does it? Let's see if the calculator says it's negative 9/7. I'm hoping so. Uh-oh. I don't know where we're going to see it. Over here. Let's see. Okay. On top, so I'm going to go with alpha y equals, just for safety on this one, negative 3 log 125. On the bottom I've got log 125 minus 2 log 125. Same thing. Now, of course, was this process the better way to go? No, I told you at the beginning, if they're powers of the same family, that's definitely the way to go. This, though, isn't hard unless you make it hard. As long as you're clear on what's a number and what's not a number, this is a super easy algebra problem. From right here, you've just got x plus 3 times a number equals something x. That's it. It looks weird. It's not. So let's do one last or two last questions before we wrap up today. So I thought I'd do one simple application. So what if we have a bacteria culture that doubles in size every hour? How many hours before it exceeds 1 million bacteria? We can model this like we've done before, right? So like the beginning of time, how many bacteria? I guess they've got to tell us, so let's assume since they didn't say that they meant that there's one. And then in an hour, how many are there? 2, it's doubling. And then in 2 hours, how many? 4 in 3 hours. 8 in 4 hours. 16. If we keep going, in T hours, we're going to have how many bacteria?
Billion.
Now we can keep going forever. I need to express this.
What is on?
These are powers of 2, right?
Yeah.
So go powers of 2. If you instead wanted to think of that as like the initial amount times 1 plus r to the t. Do it it that way too. The initial amount is just 1. If it's doubling, you take 100% and add another 100%, so you end up with 2 to the t. So a couple different ways to think about that. Yeah? We want to know when it's more than 1,000,000 though. So in other words, I want to know when 2t is more than this. This is what we've been waiting for. We could graph it, but I'm not going to graph it. That's so much longer. How do we get t's down? Logarithm. How to bring that t down to the front? Oh, except I messed something up. It's the logarithm of 1,000,000. What's the logarithm base 10 of 1,000,000? Six. Yeah? Log base 10 of 10 is 1. Log base 10 of 100 is 2. Log base 10 of 1,000 is 3. Log base 10 of 1,000,000 is 6. Okay? So the last step here is say t is greater than 6. And if I want t by itself, I've got to divide by log of 2. And there you go. So I'll do that with my calculator. Take 6, divide by the log of 2. And there you go. So this population is going to exceed 1,000,000 after t exceeds 19.932 units. Hours. So there we go. Those are all like Algebra 2 problems. I want to look at one that's, well, still an Algebra 2 problem, but a little bit more before we quit today. Let's look at one more. Okay, you guys tell me what to do first. Combine the logs, how? Multiply? Right? Next step. Get rid of the logarithm. How? Exponential it with the 12. Okay. Big 12. 12 to the 1 power is 12. Remember, that's not multiply, though. This is not a linear equation that's left. All kinds of equations we learned this year can combine. It just depends on what you're given. This isn't linear anymore. It's parabolic. You'll see a couple of those in your assignment, right? Parabolic equations, we have all kinds of ways. We just spent a whole lot of time. You guys did test reflections and everything. Factor, quadratic formula. I like factor. Right. So, how about that? Does that factor? It does, luckily. 3 and 4. So we get 2 answers to this problem. The thing that makes that 0, which makes the whole thing 0, is -4. The thing that makes that 0, which makes the whole thing 0, is 3. You can get two answers to a logarithmic problem. Totally can happen. Are both of these legit? Huh?
Only the 3 come up.
Only the 3 works on this one. Why? This is an extraneous answer again. It's not really an answer. It comes up because of the solution process that we're trying to use to get it. It just pops up, but it's not really going to work. How'd you know, Mary? Negative number. You want to think a little bit more than that, though, because sometimes negative numbers could be an answer. Yeah? Sometimes they could. This time they can't. You because this is just a plain logarithm, and it has that picture from a second ago, which means its domain is 0 to infinity, and you can't put a negative number into this guy. This guy's left by 1, so it'd be okay to put a negative number in this guy if that number was like -1/2 or -3/4, but as soon as you went to like -2, that would be a problem. Okay, logarithms cannot have negative numbers in them if when the machine tries to grab it, it's still negative, right? So that's the idea. All right, we'll see you next time. We're done.